Okay, we're going to do a crash course in forces. We've got our first quarter final coming up on Thursday. There's some things you need to know about forces between now and then. First of all, in physics, a force is a push or a pull. Anytime you're pushing or pulling on something, you're putting a force on it. These forces can cause acceleration. In fact, the only cause of acceleration ever is unbalanced forces. If an object has unbalanced forces, which means the force to one side is not as strong as the force to the other side, that object is going to accelerate. The net force is the sum of all the forces on an object. If you have a force of 10 to the left and a force of 5 to the right, then your net force is going to be 10 minus the 5. So you add these tip to tail, and you end up with a net force of 5 to the left. That's your net force. Equilibrium is when all the forces add up to 0. So there's no unbalanced forces. All the forces, any downward force is balanced by an equal upward force. Any left force is balanced by an equal right force. Then an object's in equilibrium. An object in equilibrium always has 0 acceleration. That means if it's not moving, it's going to continue not to move. If it is moving, it's going to keep moving in the same direction at the same speed. It's not going to turn, it's not going to speed up, it's not going to slow down. Same speed, same direction. This is called inertia. Inertia is the tendency of an object at rest to stay at rest, and the tendency of an object in motion to continue in that same motion. We use free body diagrams to help us look at the forces on an object. There's a few easy steps to drawing a free body diagram. First, you draw a simple shape, a rectangle. If it's a round object, you can use a circle. That's going to represent your object. You're only going to draw the object, not any other things that are interacting with that object. Put a dot in the middle to represent the center of gravity of that object, and then any forces that are affecting that object will come out from that dot, that center of gravity. So we're going to draw those as vectors. Let's look at an example. Let's look at Mr. McCloy's weekend car, the Bugatti Veyron. Now, if I want to draw a free body diagram of me cruising around the streets of Revere in my Bugatti Veyron, I need to represent this as a rectangle with a dot in the middle. Now, this is not as pretty as Mr. McCloy's actual car, but it's going to get the job done for our free body diagram. Next, we've got to consider all the different forces that are affecting my car. The first force you should always put on a free body diagram is gravity. That one's a gimme. It's obvious. As long as you're on Earth or on some kind of planet, there's going to be gravity affecting you. So you represent that with a vector pointing down. Gravity pushes things down. And label it Fg for the force of gravity. My car doesn't sink down into the street, though. It doesn't sink down to the middle of the Earth. So there has to be another force balancing that force of gravity. The road is actually pushing up on my car. As gravity pushes down on the car, the road pushes up. If Mrs. McCloy gets in the car, then the car is pushing down a little bit harder on the road, so the road has to push up a little bit harder to keep it balanced vertically. Now, we've also got me pushing the gas pedal, which revs up the engine, which turns these wheels, and the wheels push me forward. So here's my force of the wheels. This is a Bugatti Veyron. Here's my force from the wheels. And that's going to have me accelerating in this direction. But that's not all the forces. This is a very aerodynamic car. It's a pretty sweet ride, I won't lie to you. But there's still going to be some wind resistance there. So we've got to have some backwards force to show that wind resistance. It's resisting me. If I stuck my hand out the window, it would push back on my hand. That's the wind resistance. You can see here that the force vertically is balanced. The force of gravity is the same length as the force of the road pushing up on the car. But here, my wheels are pushing the car forward a lot more than the wind is pushing backwards. That means that I know that this car is going to be accelerating to the left. Let's talk about some common forces that we had here. The first one, obvious one, the force of gravity. Force of gravity on an object always goes down. The more mass an object has, the more gravity pushes down on it, the bigger vector you're going to have. It goes towards the center of the planet. So that's my F of G down here. The second one's the normal force. Anytime two objects are touching each other, there's going to be a normal force that's perpendicular to that plane of contact. Here, my sweet car is sitting on the road. So this force of the road on the car is actually called the normal force. The normal force from the road to the car. It pushes up, it's perpendicular to the road. And then finally, there's a frictional force. In this case, the friction comes from the wind resistance. So, the force of friction always resists the motion of an object. If I was driving to the right, the force of the wind resistance would be to the left, in the opposite direction. Friction always opposes motion.
Shout out to you. Have a good day today. See you tomorrow in class. And you'll see us too. And you'll see us today.
So, when I get in my Bugatti, it's definitely accelerating. We have a rule, a law, a formula for how much that accelerates. Here it is. Very, very simple formula. Way better than delta y equals vyi delta t plus 1 half a delta t squared. Sigma f equals ma. Here, this symbol, you might recognize from movies about fraternities, is a sigma. It means the sum of. So here, sigma f is the sum of all the forces. Sigma is the sum of all, and then whatever comes after the sigma. So, sigma F means the sum of all forces, or the net force, measured in newtons, equals lowercase m is the mass of the object. That's measured in kilograms. And, of course, A, we should already know, that's acceleration, measured in meters per second squared. Copy and paste. Okay. Let's take a look at the free body diagram we have of my sweet ride. We've had the force of gravity pushing down on it, the normal force from the road pushing back up on the car, the force of my wheels pushing the car forward, and then we have a bit of wind resistance. Let's say the force of the wheels is 45,000 newtons. The force of the wind resistance is 5,000 newtons. And the mass of the car is 2,000 kilograms. First thing we need to do is figure out how much my force of gravity is. Remember, force equals mass times acceleration. We definitely know the acceleration due to gravity. It's 9.81 meters per second squared. We now have the mass of the car, 2,000 kilograms, so the force of gravity is going to be the mass times the acceleration of gravity, 2,000 times 9.81, $19,620 newtons. Also, the force from the road on the car is going to match that. If I had a smaller force from the road pushing up on the car would sink down into the ground. If I had a bigger force from the road on the car, it would float up into the air. So this is also 19,620 newtons, which is matched by the force of gravity. The sum of my vertical forces is going to be 0 because these two cancel each other out. The sum of my horizontal forces is not 0. So, Let's figure out this acceleration. First of all, my net force. I've got 5,000 to the right. I've got 45,000 to the left. I'm going to call the right a positive force, the left a negative force, and add those forces together. This gives me a net force of negative 45,000 plus 5,000, negative 45,000 plus 5,000, net force of negative 40,000 newtons. Plug that into my F equals ma equation. Negative 40,000 equals the mass, 2,000, times the acceleration, which is what we're looking for. A is going to come out to negative 20, which tells me the acceleration of the car is 20 meters per second to the left. Let's talk about this gravity a bit more, because I kind of glossed over that. The force of gravity is weight. So how much something weighs is how much gravity is pushing down on that object. We got force equals mass times acceleration. So the force of the gravity, the weight, is that object's mass times the acceleration due to gravity. Here on Earth, 9.81 meters per second squared down. There you go. So the weight of an object in newtons is its mass in kilograms times 9.81 meters per second squared. A 1 kilogram object has a weight of 9.81 newtons. Here's the thing though, forces come in pairs. One thing that you'll be learning in November is that for every action there's an equal and opposite reaction. So when the Earth is pulling down on, say, a baseball in Game 5 of the World Series, the Earth pulls down on that ball, the ball also pulls up on the Earth. It's the same amount of force on the ball as it is on the Earth, but the Earth has a way bigger mass. So because the Earth's mass is so big, the acceleration is teeny tiny, can't even measure it, it's so small. So the Earth is accelerating upwards towards that baseball, but not very much. That's pretty much all the force information that's going to be on Thursday's midterm. Good luck.